Under Rydberg equation, this is the continuation from where I start from energy quantization. It's already on my channel if you want to watch it. Under Rydberg equation, this is a very important part of energy quantization, how energy or electron move from one energy level to another. Remember, for an electron to move from a lower orbit to the higher one, it has to absorb electron. But for an electron to move from a higher level to a lower one, it loses energy. But for an electron to absorb, to move from lower to the higher, it has to absorb energy. And under this Rydberg equation, I'll concentrate mostly on the calculation aspect. But then, a quick introduction. If the first law of under energy quantization, I've already explained this using the Bohr model atom is on my channel. If an electron should move from, let me say I have an energy level this, I have an energy level like this. Now when an electron moves from one energy level, which is principal quantum number 1, here principal quantum number 2, principal quantum number. So once an electron, let's say from this 2 comes down to 1 here, the principal quantum number, this one is assigned, we used to call it the Lyman series. Here is the Balmer series. Here is the Patchan series. Here is the bracket series, and here is the P-fund series. So an electron can draw from here to this one. So we are talking about the Lyman series. If an electron draw from any level and end up in 2, we're talking about the Balmer. If an electron leave here and stop at 3, we're talking about the Patchan series. If it leaves from here and drop in the energy level 4, that is the bracket series. The drop at the energy number 5, that is the P-fund series. Now there's a very big examination question for everybody, O-level, JAM, WAEC. Please know this very well. The Lyman series is associated with the UV, the ultraviolet light. The ultraviolet light. Note it very well, the Lyman series. Why the Balmer series is visible, is actually associated with visible light. This is the visible light. Now these 3 are associated with what are called the infrared light. The infrared light. Now there is a question I saw in the past question. They asked, so I don't have time to write it. Write it down, and you know. They asked, which of the following electron transition will emit a photon in the visible light spectrum? I'll repeat again. Which of the following electron transitions will emit a photon in the visible light spectrum? Of course, the only one that emits an electron in the visible light spectrum is the Balmer series. So that's an exam question. That's why I'm taking my time to let you know all this equation. Now, having introduced this topic, I'm going to go to the main calculation proper and what it is all about. And this first example, for the Balmer series, calculate the wavelength for n is equals to 3, and 2, the frequency for n is equals to 3. And this is the formula. This is the Rydberg equation, and this is the Rydberg constant, and it's a constant. Look at the value here. You should commit it to memory. And this is the formula. Why this lambda is the wavelength. Now this is the initial. This is the final. And there is a thing I said you should note here. Note that always n2, the value of n2 must be greater than n1. And so for the Balmer series, remember we did the Lyman series, the Balmer series. I just talked about the bracket, the P-fund series, the Patchan series. And so all you need to do for you to calculate the wavelength is 1 all over wavelength, and you have your Rydberg equation to be, so if your first energy level, the Balmer series is 2. We talked about it, the Lyman, the Balmers, and at n equals to 1, it is the Lyman series. At n equals to 2, Balmers. At n equals to 3, we talk about Patchan, the bracket n equals to 4, and the rest. So immediately we have Balmer, that means n is equals to 2. That means the first one and n equals to 2. So this is 2 square minus. I told you that your n2 must be greater. So your n2 is already even given is 1 all over 3 square. So here is 1 all over 4. 1 all over 4 minus 1 all over 9, and if you punch it in your calculator, I don't want to waste time in this at all. So if you punch it in your calculator, what you should get is 1 all over lambda should give you 1.523 times 10 raised to the power of 6. Please note this thing very well so that you will not fail it. Oftentimes, immediately students get this, they will say is the answer, but that's not the answer. This is 1 all over lambda. I did not ask you to get 1 all over lambda. I asked you to calculate lambda. So this, for you to calculate lambda, is have to be the inverse. 1.523 times 10 raised to the power of 6. That means 1 all over 8 is the inverse. I didn't ask you to calculate 1 over lambda, but lambda. So if you should punch that, press the inverse of that. If you press the inverse, what you should get is 6. What you will get as the answer is 6.565 times 10 raised to the power of minus 7. That's what you should get as your answer. And remember, this is in meter, the inverse of a meter, and so once you revise it, your answer will turn to meter. So the answer is in meters. So that is it. That should be your answer. Now, the second question, they ask you to calculate the frequency. Please remember that the formula for frequency, velocity is frequency all over lambda, right? And so from here, the frequency is, I want to make frequency sort of the formula, that is velocity all over lambda. And the velocity we're talking about is that of the speed of light, which is 3 times 10 to the power of 8. Having calculated this, which was 6.58565 times 10 raised to the power of minus 7. Now, if you punch this in your calculator, you get the answer to your frequency. You get the answer to your frequency, which is 4.56 times 10 to the power of 14. 4.56 times 10 to the power of 14 hertz. So that is the answer to that one. That's the answer to that one. And another beautiful question we have is the number 2 there. They said calculate the wavelength and frequency of the third line in the Patchan series of hydrogen. Please pay very attention to this, to the third line. Now, if you don't even know the Patchan is number what, you will not be able to answer this at all. You cannot be able to answer it. Remember, from the introduction of the video, I told you that the Patchan series is number 3. And I'm talking about the third line. It means that after that 3, you should add more 3 lines. So after 3, you add more 3, what you get is 6. Are you getting me? So that means automatically that your N1 is equals to 2 and your N2 is equals to 6. So put it, solve it, please. 1 all over N1 square minus 1 all over N2 square. So put it, solve it. If you can, pause the video and solve it, please. So this is easy. You already know this is 10, 9, 6, 7, 7, 5, 8. And then of course here is 1 all over lambda, and then you have 1 all over 3 square minus 1 all over 6 square. Punch everything in your calculator very fast. You will come. Don't forget this. Never forget it. That's the problem people used to have. Never. And for people in Uniport, if you have an exam that is sub OBJ and you come to this way, you didn't get the inverse, that means you have failed it. So be careful about that very well. If you should punch it in calculator, what you should get is 9.13980 times 10 raised to the power of 5 meter per meter. Then inversing it is 1 all over 9.13980 times 10 raised to the power of 5. So you should get your answer in meter now. So if you should invert it, what you should get as your answer is times 10 raised to the power of 9 meters. So that is the wavelength. Please pay attention. Always remember that you have to do inverse whenever we are talking about this. So pay very cool attention when it comes to this topic. The example number 3, an AM radio broadcast 70.1 kilowatts. What is the wavelength of the radio waves in meters and the energy? So this example I saw, remember I said that velocity is equal to F lambda. So they want to get the wavelength. So wavelength is velocity all over frequency. Now it broadcasts at kilohertz. The velocity is always that of the light ray times 10 raised to the power of 8. All over the kilohertz is 70.1 times 10 raised to the power of 3 to convert kilohertz to hertz. So whatever you get should be your answer. This is so easy. So whatever you get, you should get 3330 meters. So that is the answer to that one, 330 meters. Now the next thing you are asked to solve is the energy. Remember that energy is equal to hv. Why h is the Planck constant and v is your velocity of light, right? So your Planck constant is 6.63 times 10 raised to the power minus 34, right? Yes, minus 34. Then you times it by your velocity, which is that of the light, and what you should get hf. I was thinking this is energy is hf, please, not hv. So this is hf. So and your frequency is times 70.1 times 10 raised to the power of 3. So whatever you point in your calculator, that should be your answer, please. So if you should point it, what you should get is 5.97 times 10 raised to the power of minus 29. And energy is always in joules or work done. Now please, I want to make a simple runs here. If energy is hf and v is equal to f lambda, if I make f such a formula, f is v all over lambda. So I can put this into this equation, and this will change to energy is equal to hv all over lambda. That's another equation for calculating energy under energy quantization. So please note it very well. I want to put that formula so that however they bring it, you can be able to solve it.